We are going to look at describing, exploring, and comparing data, starting with measures of center. In this chapter, we are going to look at measures of center, measures of variation, measures of relative standing, and box plots. The objectives are to summarize data using measures of central tendency. The mean, the median, the mode are the main ones. Describe data using measures of variation such as range, variance, and standard deviation. Identify the position of a data value in a set of data using various measures of position, such as percentile, decile, quartile. And also we're going to look at box plot and 5-number summaries, known also as whisker plot. What we covered so far, we looked at frequency distribution for organizing and summarizing data. We discussed frequency distributions, lower limits, upper limits, boundaries, midpoints, class width, and a procedure that involves in constructing a frequency distribution table. We looked at graphs that involve frequency distribution table known as histograms. When we come up with histograms, they may be normally distributed, that means bell-shaped, or they may be skewed to the right or to the left. We also looked at graphs that are helping understand the data better, and also graphs that they deceive. So we have those kinds. We looked at dot plots, stem plots, time series, bar graphs, Pareto charts, pie chart, polygon, ogive. We also looked at a couple of examples that are deceiving, such as non-zero vertical axis and pictographs. The main thing I want you to remember is that non-zero vertical axis is used a lot, and when you read a graph, you want to be mindful of that. We also discussed scatter plot, correlation, and regression. Scatter plot, in short, it refers to plots involving pairs. Correlation, we have a linear correlation which has a coefficient between -1 and 1. -1 means perfect correlation, so does +1, and either negatively correlated or positively correlated. What's important to remember is that correlation is simply an association. You can correlate and associate a lot of things. It doesn't mean one causes the other. So that's important to understand. And then regression line, or the best line of fit, the line that could contain all those points in essence, of course, okay, and can summarize those. Now there is a way to come up with that. And all of this will be discussed with more details in the later chapters. Now here's the new chapter we're going to get started with, measures of center. The concept, first and foremost, is to obtain a value that measures the center of a data set, present and interpret measures of center, including a mean and median. This is the summary that we're going to look at. The idea of measure of central tendency refers normally to the following: finding the mean, median, mode, mid-range, weighted mean. A measure of center, in general, referring to a value at the center or middle of a data set. Let's start with the one that I think everybody is familiar with, known as the mean or arithmetic mean. Sometimes we refer to as average, but normally in statistics we use the terminology the mean. So the mean or arithmetic mean of a set of data is the measure of center found by adding all of the data values and dividing the total by the number of data values. Simply put, add them up, divide by size. Important properties.
Sample means drawn from the same population tend to vary less than other measures of center. The mean of a data set uses every data value. The disadvantage of the mean is that just one extreme value outlier can change the value of the mean substantially. Using the following definition, we say that the mean is not resistant. Resistant. A statistic is resistant if the presence of extreme values or outliers does not cause it to change very much.
So in short, what really happens here is that, remember the basic way we calculate the mean, and because we include every piece of data, then it is affected by outliers. And that's why I mentioned before that sometimes we use what's called a trimmed data, where we cut the top and the bottom 5%. Remember, that's in case it's doable and we have enough data. All right, let's look at the symbols that are used here. This is to make sure everybody's comfortable with the notations. The first one, obviously, is the summation notation. Everybody remembers that from algebra. Normally, we use X to represent the variable, an individual piece of data. N is the sample size, lowercase n. And we use capital N to represent the population size. So what happens in statistics, the way we use the symbols are different, and that's important for everybody to know that. And later on, it becomes extremely important for everybody to see how this thing plays out. So it's important to understand the symbol. So having said that, X bar is the symbol that is used for sample mean. So what we use Latin to represent symbols of sample, whether it's sample mean or sample standard deviation, so on and so forth. You'll see it as we come across it. Whereas for the population, we use the Greek letters. So in this case, we use mu. Mu is pronounced mu, mu, and is the mean of all values in population. So again, what really is important for everyone to know, because we want to distinguish between a sample and a population, we also use different notations. That is extremely important.
The data represents the number of days off per year for a sample of individuals selected from 9 different countries. Find the mean.
We want to find the mean. And if you look at the top right, I have given you the formulas. You are, I think, familiar with the concept. You know how to find the mean. But it is important to know that it is a sample, okay, just a few, and therefore we use X bar or summation of X over. Now this is a very simple calculation. Simply put, add them up, divide by size. So we add them up and we divide by 9. And again, you may have 2 days off, 5 days off, 10 days off, 15 days off, or I don't know, 100 days off. But on the average, we can say we have 30.7 days off. I've mentioned that before. Again, you can't say I have 2.5 cars, but you can say an American household has 2.5 cars on the average. So that's important to understand as far as how we can use this. So with that being the case, one thing I want to also mention is that sometimes they use lowercase, sometimes they use uppercase for the X bar, depending on the text that you're using. Median.
Median. The median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. In other words, the median is the midpoint of the data array.
So that's the definition of a median, just middle of the data if it's ranked from small to large.
The median does not change by large amounts when we include just a few extreme values. So the median is a resistant measure of center. The median does not directly use every data value. For example, if the largest value is changed to a much larger value, the median does not change.
Yeah, that's why they call it resistant. That's why in many cases they may use a median to discuss things, for example, the average income or the average cost of a house, because there are definitely outliers. So in those cases, for example, normally they use the median. And finally,
to find the median, first sort the data in ascending order. If the number of data values is odd, the median is the number located in the exact middle of the sorted list. If the number of data values is even, the median is found by computing the mean of the two middle numbers in the sorted list. Given the data speeds 38.5, 55.6, 22.4, 14.1, and 23.1, all in megabits per second, find A, the mean, and B, the median.
So we want to find the mean. We do have the formula at top. We use the x bar equals summation of x over n. It's a simple calculation. All we have to do, add them up, divide by the size. There are 5 pieces, and we get 30.74 megabits per second. Now, one of the things that I want to mention about the rounding, if you do the rounding early, you get what's called round off error. But they have a specific rounding rule. You want to follow that for the sake of getting the homework and exam questions correct. And that is normally 1 digit more than the given. If you see there is 1 decimal for the given data, so we add 1 more to find the average. All right, in order to find the median, you simply put them in order from smallest to largest. And the middle of the data is 1 number. And this is how it's calculated, class. You look at for the middle of the data, and this is a case with an odd number of data. In other words, 5 or 5001. It doesn't matter, it's odd. There is a number in the middle, and that is your median. However, if it happened to be an even number, then you don't have any number in the middle. So you find the 2 numbers in the middle, and you take their average. That's the idea that was discussed in the previous page. What is the meaning of the mode?
The mode, sometimes called the most typical case of a data set, is the value or values that occurs with the greatest frequency. The mode can be found with qualitative data. When no data value is repeated, we say there is no mode. There may be no mode, 1 mode, 2 modes, or many modes.
Okay, so mode simply means the one with the highest frequency of occurrence. That is the simplest way to define it. Mid-range?
The mid-range of a data set is the measure of center that is the value midway between the maximum and minimum values in the original data set. Because the mid-range uses only the maximum and minimum values, it is very sensitive to those extremes. So the mid-range is not resistant.
It's very straightforward. You just add up the minimum and maximum divided by 2, and it can't get any worse than that when it comes to using the outliers. That's why in practice, the mid-range is rarely used. It helps reinforce the very important point that there are several different ways to define the center of a data set. The value of the mid-range is sometimes used incorrectly for the median, so confusion can be reduced by clearly defining the mid-range along with the median. So mid-range is simply the sum of the min and max divided by 2. We are looking at the data, and we have now the same data. We added 1 more. We want to calculate mean and median, and we are adding the mode and mid-range. So the mean is very simple. We add them up and divide by size. Again, x bar, not mu, simply because we are dealing with a sample. The median, let's rank him first. When we do that, we know the size is an even number. So right here is the median. What does it mean? Between the 2 numbers. So because it's an even size, therefore we have to add them up, divide by 2. So that's how you would deal with the median when the size n is an even number. There is no mode. Why is that, class? Can anybody tell us why there is no mode?
Because no data value repeats.
Perfect. Nothing repeats. And to find the mid-range, all you have to do, add up the minimum and maximum and divide by 2. Now, here's what I want to add. This is extremely important. You don't need to sort or rank the data in order to calculate the mean. However, I suggest you do that. If the question is asking for the median, mode, and mid-range and other stuff, before even you calculate the mean, sort the data just to be on the safe side. I've seen students making a mistake with that. They would come up with the wrong median, they would come up with the wrong mid-range and range. Later on, we discuss that. So my suggestion is just to be on the safe side, even when you don't need it, rank the data. It is really helpful.
I have a question.
Sure.
Why do we have 4 significant figures for the median mid-range, but we keep it at 3 for the average?
Well, it's just the number of decimals. If you look at the data has how many decimals?
It has 1.
1. So over here, you add 1 more. And this number, even if you write it as 29.70, is the same thing, because when you divide, you get 29.7. You don't have to write it as 29.70. When you have to do the rounding, you round it to 1 more place. This is how they do it for, again, as I mentioned, for the sake of the text. I want more decimals. If you look at practice tests, I put more decimals. But this is the way they do the round.
Okay.
Now we have a different set, and we are asked to come up with the mode. It's a very straightforward question. It is already ranked. It is sorted from smallest to largest, and we can clearly see which one is the mode. So as you can see, 0.3 repeats more than anything else. Now, bear in mind, 0.6 repeats 2 times, but it doesn't mean anything. Okay, you're looking for the one with the highest frequency of occurrence. How about this case? Although it's not ranked, it's not sorted, so this one happened to happen 2 times, and this one happens 2 times. So we have 2 modes, or it's called bimodal, 2 mode. We have the following pieces of data: 0.3, 1.1, 2.4, 4.0, and 5.0. So what's going on here?
No mode.
No mode.
Simply because nothing repeats. So there is no mode. Well, this is the question that was just asked. Rounding rule. The mean, median, and mid-range should be rounded to 1 more decimal place than it occurs in the raw data. I want you to see something, and that is, this is the way in many texts they do it. In some texts may not follow that if you were doing it, but whenever you get on to do your homework and exam questions, you're going to stick with the rules they have to get 4 credit.
The mean in most cases is not an actual data value. For the mode, leave the value as it is without rounding, because values of the mode are the same as some of the original data values.
Okay, finally for this page.
Caution, never use the term average when referring to a measure of center. The word average is often used for the mean, but it is sometimes used for other measures of center. The term average is not used by statisticians, the statistics community, or professional journals.
So that's normally the case when it comes to statistics. Although we are used to it, and sometimes we use, okay, find the average, and we did that when we did it in algebra, so we want to be careful. So here's a frequency distribution table, and we want to find the mean. Let's see how it's done using a frequency distribution. Mean from a frequency distribution. Multiply each frequency by its corresponding class midpoint. Add the products and divide by sample size. This is the formula. We are adding x bar equals summation of f x sub m divided by n. Sometimes they use x, sometimes they use x sub m. Notice I am using x sub m with the formula, but if you look at the table, I have f times x. I did that on purpose, because I want you to see there are various ways, depending upon the text that you're using. They may use just X to represent the midpoint, okay? That's why if you look at the 3rd column, I called it class midpoint X. Sometimes even use M to represent the midpoint. And sometimes they use X sub M. Again, I'm telling you all of that because if you come across a case where the notations are slightly different, we don't want to be confused. Now, the idea is very simple. Remember, when it comes with the frequency distribution table, we don't have every piece of data. For example, if you look at the first class, it says between 75 and 124, there are 11 pieces of data. It could be that all of them are 75. It could be that all of them are 124, or it could be somewhere in between all over the map. We have no idea what each piece is. But I hope everybody understands the meaning of the frequency distribution table. So in calculation, we have no idea what each piece is. So the best guesstimation would be to use the midpoint. So the very first thing is we calculate the midpoints. How do we calculate the midpoints? Lower limit plus upper limit divided by 2. So for example, the first class is 75 plus 124, which is 199, divided by 2, which gives us 99.5. And by the way, I hope everybody remembers that we can easily see, if we go this route, this is from before. The width is 125 minus 75, or 124 minus 75 plus 1 unit. And the width is 50. So if the first one is 99.5, the rest of them I don't have to calculate, I add them up. I add what? The width. So I hope you see all you have to calculate is the first one, 99.5. Then it's a simple addition of 50. Now, I'm looking at this formula, and this formula says in order to calculate the mean, you have to multiply them, add them up, and divide by n. So that means now the second column must be multiplied by the third column. So 11 times 99.5, 24 times 149.5, and the rest of it. So you multiply these two, you get 1094.5, and the rest are calculated in the same manner. And what do we do now? We need to have the sum of the frequencies, n, we have it. We need to have the sum of this last column, we add them up. And so we divide the last calculation we just did, the summation of fx, which is 8025, by the total sample size n, or summation of f, this is n, and that gives us the answer. Now, a couple of very important observation before we move on. Is this going to be the same as the actual mean? Remember, what is the actual? The actual mean, you should have the original data, add them up, and divide by size. That would be the actual mean. But this result, the result of x equals 160.5 is an approximation. This is really expo. Why is that? Because it is based on the use of class midpoints, not the original values. We don't have everything there. So that's one very important observation. Now, what about the next one? Mean from a frequency distribution. Calculation is made by pretending that all sample values in each class are equal to the class midpoint. That is the assumption, and remember, that's really not a fact, but we don't have any other choices. Do you take the lower limit? Do you take the upper limit? No, a good choice would be somewhere in between, and that would be the class midpoint. Go ahead.
I just have one question for the last problem. What was the significance of using the width?
In order for you to go from one midpoint to the next, for you to move down here, you have two choices. Calculate each midpoint, meaning for the second one, 125 plus 174 divided by 2. For the third one, 175 plus 224 divided by 2. Are you following that?
Yeah.
But instead of that, isn't it faster to add the width of 50 to the first one and go all the way down?
Oh, okay. Yes. Yeah.
Does that make sense? And that's why I suggest we use that.
Okay.
Now, we're going to repeat that first for the mean just to refresh your memory. How do we find the mean? We are using the top formula. X bar is the summation of fx sub m over n. Now I'm using x sub m. Again, I'm doing this on purpose. So depending on the text, you have different variables used. So with that being the case, you need to find the midpoint for the first class. That means what? If you add these two, you get 5.5 plus 10.5, which is 16, divided by 2 is 8. Now, can anybody tell me what is the width?
5.
Very good. 10.5 minus 5.5 which is simply 5. So if the first one is 8, I don't have to calculate the next one by adding and dividing by 2. I just keep on adding 5. So I hope you see it's a lot easier to add 5 than adding them up, dividing by 2. So this is a faster method. Now we are going to multiply column 2 and column 3. So let's call it column 2, column 3 to get to column 4. So the first one is 1 times 8 is 8. The next one is 2 times 13, which is 26, and you have the rest of it. Now, when we look at the formula at the top, this formula tells us we need n. So the second column we need to add up. We need summation of the numerator fx sub m. That means the last column we need to add up. And so simply divide sum of column 4 over the sum of column 2, and that's x bar. Now, the next one, it says, what is the modal class? As far as the definition of a mode, it works the same way. Remember, the mode is what? The one with the highest frequency of occurrence. So which class? It has highest frequency. The frequency number 5 is the highest, so that class has the highest frequency because 5 is the largest number among the frequencies. So your modal class is that one. Now, what is the mode? Again, what they do, they find the midpoint of that class. We already have the midpoint. So the mode is the midpoint of the modal class. That's how it is calculated. I want to look at a very important topic, especially for students, because your GPA is calculated in this manner. So we are going to look at weighted mean, or you can call it weighted average.
Find the weighted mean of a variable. Multiply each value by its corresponding weight and divide the sum of the products by the sum of the weights.
So here's the formula. I want to make sure everybody understands why we do that. Think about this concept of a GPA that is discussed. First, let me just put up this example. We want to find the GPA for a college student who took 5 courses and received A. That's a 3 credit or 3-unit course. Another A, it's a 4-unit course. A B, a 3-unit course, so on and so forth. Okay. Now, why is it important to do the average in this manner called weighted mean? If you happen to have only 2 courses, I want to make sure we understand what's happening. If you have only 2 courses and one of them is A and one of them is B, remember A is normally used as given a value of 4.0 and B is given 3.0. So if you have one of each, one may be under the assumption that 3.5 would be a proper, but it really depends on the course. If a course was worth 5 points when you received an A, and the one that you received the B was worth 2 points, then it's not fair. And that's the idea, because it's weighted more. The weight on that 5 unit is, you can think of it as the weight as 5, whereas the 2-unit course, the weight as 2. So with that being the case, and again, A is worth 4, B is 3, and go down the road, and we have these values we should know. And look at the table that we have. The weight would be the number of units, and X is the value. So number of units and the value. So you multiply the first column, which is the weight column, by the second column, which is the value column or the X column, and you divide by the total weight. And this is how it's calculated. But what is important is what you put in the denominator is the total number of units, and you have your GPA. This is how GPA is calculated. We want to calculate the GPA here. Let's discuss the concept, because that's really what matters. That's important. And the concept is identical to the previous question. Now, understand the difference is, the table is given to us. It's a lot easier than before, because on a normal basis, you have to come up with the table. So you have to create this table. Over here, it's given to us. The weight is the number of units. And normally A is worth 4 points and the rest of it. And you go down, B is 3 points, C is 2 points, and so forth. So you have to multiply those 2 columns, and that would be the sum. You divide by the total number of units. That's how GPA is calculated. As far as the distribution is concerned, if the distribution is symmetric. So I want you to look at this one first. The mean, the median, the mode, they are all happening at the same time. Now, what happens when it's skewed? Well, the mean is affected by the outlier. So this is skewed to the right. There's an outlier towards the right. That's why the mean happens towards the tail, always. So the mean is happening towards the tail. The median is in between. The one with the largest frequency is the mode, and that would be the tallest one. Which brings us to the next topic, measures of variation. We are going to look at measures of variation. It was part of the objectives that was discussed for the whole topic of describing, exploring, and comparing data. And in the previous section, we looked at various measures of center. We looked at the mean. We use X bar for a sample mean and mu for the population mean. And also we discussed the method of finding the mean for frequency distribution tables. Median, the middle of the rank data, mode, the one with the highest frequency of occurrence. Mid-range is the sum of the minimum and maximum divided by 2. And the weighted mean, which is the summation of the weights times the values divided by the summation of the weights. And finally, if you have graphs, you should understand when you're dealing with the histogram, if it's completely symmetric, if it's normal, the mean and the median and the mode happen at the same spot. But if it's skewed, the mean is the one that follows the tails, wherever the tail goes to the right or to the left. Why? Because it is affected by outliers. In this topic, measures of variation, we are going to consider the following: range, standard deviation, and variance. Range is defined as max minus mean, and again, just like a mid-range, and you don't want to mix them up, mid-range is the sum of the two divided by 2. It is obviously not resistant to outliers. It is affected by outliers. It can't get any worse than that. Remember that, max minus mean. Then we look at the variance, standard deviation, coefficient of variance. Sometimes they call it CV, sometimes they call it CVAR, which is simply the ratio of the standard deviation to the mean. If you're looking at sample, we use S over X. If you're looking at population, we use sigma over mu. And that 100% is changing it to a percentage. Chebyshev's theorem, it refers to distributions that are not normal or in general, and it uses the formula 1 minus 1 over k squared. K is the number of standard deviations away from the mean. Empirical rule, or the normal distribution, is referring to the picture on the right side. If you start with the mean and you go 1 standard deviation away, it covers 68% of the data. If you start from the mean and you go 2 standard deviations away, it covers 95%. And if you go 3 standard deviations away, it covers almost everything, 99.7%. We also have a range rule of thumb for understanding standard deviation, which divides the range divided by 4. And the reason it does, because normally 95% is good enough for everybody. And remember, 95% means 2 standard deviations away from the mean. So that means mu plus minus 2 sigma, or S plus minus bar plus minus 2S. That would be for example. All right, range.
The range uses only the maximum and the minimum data values, so it is very sensitive to extreme values. Therefore, the range is not resistant. It does not take every value into account and does not truly reflect the variation among all of the data values.
We have 2 brands of paint, and we are testing to see how long each will last before fading. So the result is given in months. We have a sample of 6 cans. We want to find the mean and the range for each group, and then which brand will be used. So it's a simple process. If you look at brand A, you are finding the mean X bar is summation of X over N. It's a simple process. You add them up and divide by 6. And the same thing for brand B. To find the mean, add them up, divide by 6. As far as the range is concerned, for brand A, you really have to rank it, but largest number is 60 and the smallest number 10. So 60 minus 10, that is what we are going to use to calculate the range, 50. And by the way, the units are the same. 35 months is the mean, 50 months is the range. We do the same thing for brand B, and we notice that the largest number is 45 and the smallest number is at the bottom is 25. So that would be the difference between the two as far as the range is concerned. So clearly we notice they have the same mean. The average number of months that they're going to last is the same, but they have different range. The range is different for both. So which one would you buy? What do you think, class?
Brand A. Well, brand B, I would pick brand B because you know what you would get. You might have a 10-year one with brand A or a 6-year one, but you don't know.
Absolutely. It is more consistent. It's all about consistency. Brand B is more consistent. According to this calculation, brand B is more consistent. The next topic is the idea of a variance.
The variance is the average of the squares of the distance each value is from the mean. The standard deviation is the square root of the variance. The standard deviation is a measure of how spread out your data are and how much data values deviate away from the mean.
But that's how variance works, and what we are interested in is normally standard deviation, not the variance, but we need the variance to get to the standard deviation. So with that being the case, as far as the notation S represents the standard deviation for a sample, sigma represents the notation for population standard deviation. Usage and property.
To determine the spread of the data, to determine the consistency of a variable, to determine the number of data values that fall within a specified interval in a distribution, used in inferential statistics, the value of the standard deviation S is never negative. It is 0 only when all of the data values are exactly the same. Larger values of S indicate greater amounts of variation.
This is important to understand. When it comes to standard deviation is never negative, because look at the formula. You see that the top is positive, so is the bottom, and you take a square root. And the only time it becomes 0 when all data values are exactly the same. And remember, when you are producing something, product, a company, a factory is producing something, we like to have less variation. So it is optimal to have 0 standard deviation. That means product 1 and product 2 are identical. They're going to last the same in essence. That's the idea behind that. Obviously, standard deviation is affected by outliers. The units are the same, and the sample standard deviation is considered a biased estimator of the population standard deviation sigma, which means that values of a sample standard deviation do not center around the value of sigma. We'll discuss this concept of an estimator in later chapters, but here's the formulas. Let's see how it's calculated. Obviously, you can use a calculator to do the calculation, but for small data, we should be able to do it by hand, just for practice. As far as the variance is concerned, the summation of x minus mu quantity squared over n. By the way, again, x or lowercase or uppercase mean the same thing. Normally, we use the lowercase. The thing that is important is for population, understand you're using the Greek letters sigma and mu, and this is capital N. Lowercase n is used for a sample size. If you are interested in finding the standard deviation, all you have to do, take a square root of the top formula. So normally the top formula is calculated. then you take a root and it becomes a standard deviation. This is the reason it's important to distinguish between a sample and a population variance. We divide by n minus 1 instead of n when it comes to a sample variance. And in order for you to calculate the standard deviation, all you have to do is take a root. But there are two ways to calculate the sample variance. This is just the same concept as this one. It can be extended and it can be proved that this will do the job also. Sometimes it may be easier to use that one. Again, I will show you with a simple example in a moment. But generally speaking, you use technology to come up with the answer. It's important, however, to understand the methodology. By the way, for the variance, as far as the units are concerned, it's the same units as the data, but squared. But when you do the standard deviation, then you have the same units. Now, again, you calculate the variance, you take a root, and it becomes a standard deviation in both cases. So you calculate the sample variance or the population variance. You take a root, becomes a standard. In other words, you really don't have to do calculation two times. One is simply the root of the other one. Or if you're given the standard deviation, you can square it and get the variance. As you remember, we do have the formulas and tables and usage of a calculator. So I put the information here also that's handy for a TI calculator. You can enter the data as follows. Click on Stat, Edit, and you want to clear, and then type in the data in, for example, L1. Then you can check by going to 1, again, Stat, Calculate, select 1 for one variable, and type is L1. And you want to type it. And to do that, you do second 1 to type that. And you can see the summary if you scroll down. I highly recommend you guys try it on your own when you have a piece of data and you want to calculate something. See if you can use your calculator that way. You can try it. And it's fairly nice and easy. So here's a very simple example we want to look at here. We are repeating the same question, but we are finding other things in this case. We want to find the range. We have to rank the data, or in this case, maybe it's small enough even without ranking, you can see it, but it's a good practice to rank it. In order for you to find the range, you need the largest minus the smallest. The max minus mean, 55.6 is the largest, and 14.1 is the smallest. Put it in descending order or ascending order. In this case, ascending. Rank it from smallest to largest to be on the safe side. To calculate the standard deviation, take a look at the formula. We need to find x bar. Therefore, let's find x bar. What is x bar? Add them up, divide by size. And we have the answer. Now, what about standard deviation? You can just find the variance and then take a root, or you can put it under the radical in one shot. It really is up to you. It doesn't make any difference. We are interested in calculating S. Why is this S? And that's important for everybody to realize. You're looking at a small piece of data. It's only 5 pieces of data. If you look at the formula, summation of x minus x bar, that means every piece in your data. Look at the data. The very first one is 38.5. So 38.5 minus 30.7 has to be squared. And this is why the standard deviation or variance for that matter, it's non-negative. Can it be 0? Yes. All values are the same, it can be 0. But can it be negative? Absolutely not. Why not? Because the numerator is positive. Why is it positive? Because it's the sum of the square of numbers. The denominator is positive. Why is that? Because it's the sample size minus 1, which is still a positive. So with that being the case, all you have to do, 38.5 minus 30.74, square it, plus 55.6 minus 30.74, square it, and all the way to the end, and divide by n minus 1, 5 minus 1. If you take a root, we have the standard deviation. Calculation in this manner is not a big deal. I will show you a different calculation too. because I want you to be exposed to it. You should know how it's calculated by hand, but if we have too many, the data size is large, we can use the technology. Now, here's what I mean by many decimals. It is important to keep the numerator with many decimals. You divide by 4, you take a root, and eventually you do the rounding. So you don't want to do the rounding too early. If you put the numerator the 4 decimals with only 2 decimals, then your result here may be wrong. So your standard deviation is 16.45. If somebody is asking, what is the variance? It's the same thing squared, 16.45 squared. Normally, we are not interested in variance. In many cases, in order to get to it, it's easier to just not to write the root, calculate the variance, and then take it. So this is the method that we are simply subtracting the mean from each piece of data. We square them, we add them up, and divide by n minus 1. We're taking the average of the differences. So with that being the case, here's the second method I want you to see quickly. If you recall and you go back to the formulas, another way of calculating this was the square root of n summation of x squared minus summation of x quantity squared over n times n minus 1. Now, I want to make sure everybody understands the meaning of summation of x squared and summation of x quantity squared. We don't want to mix them up. So I'm going to write down the summation of x squared. Summation of x squared means 38.5 squared plus 55.6 squared all the way to the last one. That is the summation of x squared. However, summation of x squared means add them up, 38.5, 55.6, all the way to the last entry, and now square that. So I'm mentioning that because I want to make sure we know how we calculate each one, and we don't want to mix them up. Summation of x squared versus summation of x quantity squared. Again, two different methods of calculation. You choose the one that works for you. I expect you to be able to do it on your own for small sample data. We're going to get another example. You want to find the variance and standard deviation, and it's telling us we are dealing with the population. Let's assume it's the population. Therefore, we are going to use the sigma and mu. So first thing first, you need to calculate the mu. Add them up, divide by size, and we get 35. In order to find sigma squared, you want summation of x minus mu quantity squared divided by n. Summation of x minus mu quantity squared. So let's calculate x minus mu. So the first one would be 10 minus 35. The next one would be 60 minus 35. And the next one would be 50 minus 35. And here's the column, which is the third column. Now, the fourth column will square the third column. So negative 25, square it, 625. And do the same thing with the rest of them. And we need to add them up. So this is x minus mu squared for each case. Now the summation would be to add up this one. And what you are looking at, this one, is the following summation. Summation of x minus mu quantity squared. In other words, this is the numerator of the variance. For mu class, please change it to 6. That is the variance. Standard deviation, you just take a root. So you take a root, and that would be the standard deviation.
Find the variance and standard deviation for the amount of European auto sales for a sample of 6 years. The data are in millions of dollars.
It's important to pay attention that this is a sample. The variance S squared is summation of x minus x bar quantity squared over n minus 1, or n summation of x squared minus summation of x quantity squared over n times n minus 1. There are two different ways of calculation. Let's look at this method of calculation. Again, for practice, we are looking at various types. Needless to say, as you've seen, in all cases, we are using a small size data because we want it to be manageable when we do it by hand. And so if you look at the formula, the numerator needs the summation of x squared and then summation of x quantity squared. So first, let's square the first column. So we get 11.2 squared, 125.44, and you move on with the rest. Now, when you add up, this one is summation of x when you add up the first column. Now, when you add up the second column, this one is summation of x squared. And so we put that into the formula. And remember, n is 6, by the way. N, which is 6 times 958.94 minus 75.6 quantity squared divided by n times n minus 1, 6 times 5. And it gives us s squared. To calculate s, all we have to do, take a root. So the standard deviation is 1.13 in millions of dollars, $1.13 million. We looked at calculation of standard deviation and variance for a few cases, small sample size on purpose. Range rule of thumb.
The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values, lie within 2 standard deviations of the mean.
So that's why it's used as a standard, if you will, mu plus minus 2 sigma, or for a sample would be x bar plus minus 2s. If it's beyond those two, or if it's less than mu minus 2 sigma, or if it's greater than mu plus 2 sigma, those are considered unusual. So if it's unusually high or low.
To roughly estimate the standard deviation from a collection of known sample data, when the distribution is unimodal and approximately symmetric, use S as approximately range over 4.
This distance from here, if you will, to here is 4 sigma. And if that is the case, and you normally don't have access to the population, normally we don't have access to the population standard deviation, we can, if we have that range, we can divide it by 4, and that would be the standard deviation we are going to use. And so range rule of thumb, mu plus minus 2 sigma, range rule of thumb. Within that, and if it's other than that, beyond that, it's unusual. Usual within mu plus minus 2 sigma. This graph was given in the beginning when we discussed the synopsis of what we did. This is known as the empirical rule.
The empirical rule states that for data sets having a distribution that is approximately bell-shaped, the following properties apply. About 68% of all values fall within 1 standard deviation of the mean. About 95% of all values fall within 2 standard deviations of the mean. About 99.7% of all values fall within 3 standard deviations of the mean.
Those are the numbers we come across often, especially when we go to normal distribution and deal with later chapters. We should be familiar with these numbers. Empirical rule applies to a bell-shaped, a symmetric, and normal distribution. Otherwise, it doesn't apply. And that's why the Chebyshev's theorem was discussed, and we're going to look at that also. Now, according to the empirical rule, when you start from the mean and you go 1 standard deviation over on each side, that's 1s, if you will, or 1 sigma if it's mu. That covers about 68% of the data. 2 standard deviations, 95%, 3 almost all, 99.7%. And why is this important? If you're producing something, if your target is such that you want to target 95% of the population, then you are not going to go beyond 2 standard deviation because the cost may not make it worth it. If you want to go more than that, if you want to target more than that, if you go within 3 standard deviations, you cover almost everyone, 99.7%. So that is really an important piece of information, and you're supposed to know those values. IQ scores have a bell shape. So it is mentioned that you are dealing with an empirical rule. with a mu of 100, mean is 100, so that's mu, and sigma is 15. Mu is 100, sigma is 15. What percentage of IQ scores are between 70 and 130? Now, this is really referring to the previous page. All you have to figure out is how many standard deviations away from the mean are the two numbers. Now, I want to show you an easy way of approaching this, and then we look at the calculation also. So if you are dealing with this, the concept is very simple. You have the mean. We're going to go to the left, and we're going to go to the right. To the left is number 70. To the right is 130. Now, as you all see, the difference in both sides is 30 units. It's clear. 130 minus 100 is 30, 100 minus 70 is 30. So on each side, we go 30 units. Now, 30 units really doesn't mean anything. What matters is that what does it translate into, meaning how many standard deviations. So the distance of 30 is not good enough. We want to know it corresponds to how many standard deviations. And because the standard deviation is 15, 2 times 15 is 30, so it corresponds to 2 standard deviations. It corresponds to 2 standard deviations away from the mean on both sides. And therefore, now you have the answer, which is 95%, according to empirical rule. We want to approximate the lowest value and the highest value in a data set where X bar is given as 10 and R is given as 12. Remember, we want to go with mu plus minus 2 sigma or X bar plus minus 2S. That's the idea. And so S, if you go back to the range rule of thumb, we said because we say plus minus 2 sigma is the total of 4 standard deviations. R, the range is given. If we divide it by 4, it gives us an approximation for S. And so X bar plus minus 2S gives us the answer. 10 plus minus 2 times S3. So 10 minus 6, 10 plus 6, and that gives us the low of 4, high of 16. So this is empirical rule, range rule of thumb, which refers to starting from the mean, you go 1 standard deviation, or 2 standard deviations, or 3 standard deviations, what happens? That's the idea. The 2 standard deviation is considered a range rule of thumb and good enough for most everything.
Professor, I just have a quick question.
Sure.
I'm just trying to keep track of all the variables and all the symbols. What is the X with the line over it symbolize?
X bar represents the sample mean.
Sample mean. Okay, gotcha.
X bar sample mean, mu is population mean. Chebyshev's theorem, the proportion of values from any data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is a number greater than 1, and it may not necessarily be an integer. In the table, I'm showing you the calculation for a couple of them. For example, if k equals 2, 1 minus 1 over 2 squared is 1 minus 1/4 is 3/4, and it corresponds to 75%. So I'm just discussing this one. 2 standard deviations mean k is 2, square root is 4, 1 over 4, subtract that number from 1 is 3/4, is 75%. 3 standard deviations away, 3 square root becomes 9, 1 over 9 subtracted from 9 is 8 over 9, precisely about 88.89%, so on and so forth. When do you use that? When the data is given and we don't know anything about it.
The mean price of houses in a certain neighborhood is $50,000 and the standard deviation is $10,000. Find the price range for which at least 75% of the houses will sell.
If we look at the table, we really don't have to do much. 75% corresponds to 2 standard deviations as far as the Chebyshev's theorem is concerned, that at least 75% happen within 2 standard deviations of the mean. So we are going to do the calculation. Are we using X bar or mu? Which one is which? Is it a sample? Which one is that and why?
Isn't it mu because we're just looking at the houses in that specific neighborhood?
Exactly. It refers to all. Here's how you know it's a population. Population refers to all somehow. This doesn't say the mean price of houses, 10 houses in the neighborhood, or 20 houses, or even 200 houses. It says the mean price of houses in a certain neighborhood. That means all. That means mu is 50 and sigma is 10K. And you're looking at mu plus minus 2 sigma. It is extremely important to know it is referring to population. What we need to know now, why Chebyshev's theorem?
Oh, I was just gonna say that it's because it's asking how many, like, find the price range of for at least 75% of the houses will sell. So therefore, we want to know like a certain percentage of the range that we have. So therefore, we need to be able to find like the values that will be within that 75%. So then that's why we use Chebyshev's theorem.
But why Chebyshev's? Why not empirical rule? We use Chebyshev's theorem when we don't know anything about the distribution. The distribution is not mentioned to be normal. By that, therefore, we have to use Chebyshev's theorem. That's important to see. Chebyshev's theorem because we don't know about anything about the distribution of the prices.
A survey of local companies found that the mean amount of travel allowance for executives was 25 cents per mile. The standard deviation was 0.02. Using Cheby's theorem, find the minimum percentage of the data values that will fall between 20 cents and 30.
We know it's 1 minus 1 over k squared. So the standard deviation is given, 0.02, and the mean is given. So we need to know how far we are from the mean. And again, it is asking for Chebyshev's theorem. But if it wasn't, we should know it's using Chebyshev's theorem because it doesn't say anything about the distribution being normal. So with that being the case, you need to know how far you go to get to that number. So look at this one. This way, to the left of it is 0. To the right of it is 0.3. And the distance between those two numbers and 0.25, which is the same, by the way, it should be the same for you to come up with the answer, has to be divided by sigma to give us k, the number of standard deviations. So 0.3 minus 0.25 or 0.25 minus 0.2, they give us the same answer. In both cases, the answer is 0.05. You divide by the standard deviation sigma to get to k, and that's 2.5. Now, according to Chebyshev's theorem, we say 1 minus 1 over k squared. So 1 minus 1 over 2.5 squared. Now you need to calculate this and subtract it from 1. And that works out to be about 84%. Comparing variation in different samples or population, we use what's called coefficient of variance. They call it CV or CVR or COVR, depending on the text. It is the ratio of the standard deviation to the mean, and then you can change it to a percentage. So coefficient of variance is defined for a set of non-negative sample or population expressed as a percent, describes the standard deviation relative to the mean and is given by the following. So standard deviation divided by the mean expressed as a percentage. And as I mentioned, CVAR or CV, sometimes COV. The short notation CV is good enough. When the units are different, normally that's a good thing to check. So let's look at the example of that. The mean of the number of sales of cars over a 3-month period is given as 87. This is mu, all cars over the course of 3 months. And the standard deviation sigma is 5. So that's for the cars. For commission, the mean is 5,225 and the standard deviation is $773. We want to compare the variation of the two. There are two different things completely. So we want to compare coefficient of variance. So with that being the case, the first one, this would be mu, this would be sigma. For cars, this would be mu, this would be sigma for commissions. So we divide the standard deviation by the mean, and then we change it to a percentage. So car sales, the number of cars, if you will, okay, the percentage, you can say car sales. And for commission, 773 divided by 52.25. And again, it's changing to, it is extremely important that you write it as, if you wrote it as 14.8 or 5.7 is wrong, you can, even if you left it as a fraction, I'm okay with that, but understand they want it in percentage. If you left it as 14.8, it is wrong. And so that's extremely important to understand. So with that being the case, when you compare, the second one is larger and second one has more variation. So commissions are more variable than sales, of course. All right, the next topic is measures of relative standing and box plots. We discussed measures of center, such as mean, mode, mid-range, weighted mean. Measures of variation, such as range, variance, standard deviation, coefficient of variance. We also looked at the empirical rule, the range rule of thumb, and Chebyshev's theorem. We also looked at their formulas and different notations, and it's extremely important to see that when you are dealing with a question, you have to realize whether you're dealing with a sample or a population. So you want to make sure you use the proper notation. Measures of relative standing and box plots. The key concept in this section gives us measures of relative standings, which are numbers showing the location of data relative to others within the same data. So here's the synopsis of what's coming up, the z-score. When you ask your instructor, are you going to curve the grade, you're referring to z-score is defined as x minus x bar over s or x minus mu over sigma. Percentile, it's calculated as the number of values below a specific number divided by a total number of values. That 100% just changes it to a percentage. Percentile locator, notice we use L. In some cases, I've seen that they use C. N is sample size, but notice K over 100 or P over 100. A percentile, in many texts, they use P. In some cases, they use K. So again, I want to make sure that you're familiar with various notations. Quartiles separates the data into 4 equal groups, Q1 or P25. Q2 is the same as the median, and Q3 is P75. Outlier. How do we find an outlier? I've mentioned the concept of outlier before, which means something is way off, but now precisely a value which is less than Q1 minus 1.5 IQR or Q3 plus 1.5 IQR. We see what that means shortly when we look at box plots and 5-number summary, which requires 5 numbers minimum, those 3 values, and the max. What is a z-score? A z-score or standard score is the number of standard deviations that a given value is above or below the mean. It is obtained by subtracting the mean from the value and dividing by the standard deviation. So pay attention to the formula z equals x minus x bar over s, or z equals x minus mu over sigma. The important properties of the z-scores.
The z-score is the number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as numbers with no units of measurement. A data value is significantly low if its z-score is less than or equal to -2, or the value is significantly high if its z-score is greater than or equal to +2. If an individual data value is less than the mean, its corresponding z-score is a negative number.
If your z-score is 0, that means your score is the same as the average in class. If your z-score is positive, that means above the average in class. If it's negative, it means below the x-axis. Okay, that's the bottom line. And that 2 and -2 that you see, remember mu plus minus 2 sigma to the right, 2 sigma to the left. Those are the concept. that we've seen. Okay, so the same thing that was discussed previously as far as the empirical rule and the range rule of thumb is concerned. Let's see what we mean by that. Let's start with a very simple example.
Which of the following two data values is more extreme relative to the data set from which it came? The 400-gram weight of a baby, n equals 400, x bar is equal to 3,152.0 grams, s equal to 693.4 grams. The 99-degree Fahrenheit temperature of an adult, n is equal to 106, x bar is equal to 98.20 degrees Fahrenheit, and S is equal to 0.62 degrees Fahrenheit.
It's very simple. We have to put that into the formula, okay? And the top right formulas in blue give us the z-score and how we calculate it. They are very similar, x minus x bar over S or x minus mu over sigma. We are dealing with a sample. We use the first one. If by any chance you're saying you're using the second one, the numbers work out the same, and in this case, it doesn't make that much of a difference. But it does make a difference in other cases, so you want to be careful using the proper formulas. So for the babies, so you're going to put x minus x bar over. So you put in simply the numbers, and you end up with 4,000 grams minus 3,152 divided by S, which is 693.4. Now, notice N is 400, but doesn't come to play. N is just a piece of information. It's important to know the sample size. It doesn't come to play here. And you have the answer. The second one, the X value is 99 minus X bar, 98.2, divided by S, which is 0.62, 98.2, and you calculate it. And obviously the second one is larger, has a larger z-score, which is the temperature. Sounds good. Just make sure that number is changed to 98.2. Here's the next one.
A student scored 65 on a calculus test that had a mean of 50 and a standard deviation of 10. She scored 30 on a history test with a mean of 25 and a standard deviation of 5. Compare her relative positions on the two tests.
You have to calculate the z-score. What is the score? If you look at the first one is 65, that's the score, x. The mean and the standard deviation, that's the first one, you calculate it. The next one is 30, so this is the x amount, if you will, the score. The mean is 25, so mu is 25, standard deviation. And you calculate that, and you end up with 1. Therefore, which one is higher? Clearly, according to the z-score, the first one. Let's look at one more similar example for the z-score.
The lowest platelet count in a data set is 75. Platelet counts are measured in 1,000 cells per microliter. Is this significantly low? X bar equals 239.4, S equals 64.2.
Okay, so we just used the z-score to figure out what's going on. According to the z-score, x minus x bar over s. This is the value we use for x. So we do this simple calculation, and it gives us negative 2.56. Now, first of all, it's on the negative side, and that's why they are asking if it's significantly low. Let's assume instead of 75, we had a larger number and it ends up being positive. They would ask, is it significantly high if it's positive, okay? Now, if you recall, the range rule of thumb says mu plus minus 2 sigma is fine and beyond is unusual. If this number is larger than 2 or smaller than negative 2 is unusual. That's basically it. So you have your answer there. Z is less than negative 2 and therefore is significantly low. Why we are saying it's significantly low or significantly high? We are comparing it to two numbers. One of them is negative 2, one of them is positive 2. So less than negative 2 and larger than, or if you will, I should say, larger than 2 it's considered unusual.
Percentiles are measures of location denoted P1, P2, P, etc., P99, which divide a set of data into 100 groups with about 1% of the values in each group. Percentiles separate the data set into 100 equal groups. A percentile rank for a datum represents the percentage of data values below the datum. Round the result to the nearest whole number.
Here's how the percentile works. Number of values below X divided by the total number of values. Now that 100% just changes it to percentage. I want you to see the concept. What's important is to see this one. In some texts, they use that and they add 0.5. Why am I giving you that formula? And that's not the formula that we use in this text. In some texts they do, and I want to mention that some of this stuff in stats calculated slightly different. If you use different technologies, sometimes you come up with different answers, but they differ by a little bit, just to let you know. However, for a large N, for a large size of data, they're almost identical. N is the total number of values or the sample size or even the population size. K is the percentile. Like P sub K, if you will. L is the locator. Where is it located? For example, for 12th value in the sorted list, remember it has to be sorted. L is 12, and PK or kth percentile example, P25 is the 25th percentile. Now look at the formula. We can say K over 100 times N or P over 100 times. And remember, that K over 100 is that really the percent format of the K. So when we say 25th percentile, just as an example, 25th percentile, that means 25 over 100. So if you're looking at 25th percentile, that means what? 25 over 100. That's the meaning of K over 100. Notice in the next formula, I say P over 100. Depends on the text, but understand if you come across a different format, you don't want to be thrown off. So with that being the case, let's start with this simple example. We have 50 cell phone data speeds as follows and are arranged in increasing order. I want to make sure everybody pays attention to this because if it's not, you have to do that. So this must be arranged. Because this contains 50 pieces, that's a lot, and we don't want to waste time. It may not be given to you in this format. You have to arrange it, but this is given in arranged format. It is ranked, and therefore it makes life easy. So that's the first thing I want everybody to notice. And so for number 11.8, we want to find the percentile for 11.8. And the top gives us the formulas that were given. Percentile refers to the number of values below a specific number. Look at the top, says below X. What is X in this case is 11.8, everybody. Divided by the total number of values. So where is that number? It's 11.8 here. So the rest of them, the first row and the second row are smaller than 11.8. And in each row, we put 10 numbers, class, to make life easier, 10 numbers in each row. So we have a total number of what? 10 plus 10, 20 numbers that are smaller. So really, I want you to see this number. This is what I'm interested in. This is really your answer. Now, the rest is changing it to a percentage. In other words, your answer is 2/5. So the number of values below 11.8 divided by n, total size, that's really your answer. So the answer is 2/5. Because it says percentile, we change it to a percent, that's all. That's why that 100%. So with that being the case, here's the interpretation. A data speed of 11.8 megabit per second is in the 40th percentile and separates the lowest 40% of values from the highest, now 100 minus 40, 60% of values. So we have P40, P sub 40 equals 11.8. All right, we're going to go to the next one. We want to find the 20th percentile and then 87th. So we are looking at the same piece of data. So we're going to look at part A. We are repeating the same question essentially. You can think of continuation of the same question. So look at the formula at top. L equals K over 100 times N, or P over 100 times N. We want to locate that. So here's the procedure. You want to rank the data. It is ranked already. We want to find index or locator. So they call it locator or they call it index. L, which is K over 100 times N. K is the percentage, or P, K or P, whatever you want to call it. And N is the sample size. So I don't want to get hooked up with those variables because depending on the text, they use different variables. And so L is not a whole number, rounded up. If it's 2.1 or 2.9, makes no difference. You go to the next number, which is number 3, the third one. So it's not a whole number. 14.1 or 14.5 or 14.7. You go up to the next one. That's the idea. If it's a whole number, the K percentile is the average of that value and the next one in your data. So this is the methodology. Again, this is something that statisticians have come up with. They don't agree on that 100%. That's why sometimes you see that 0.5 being added. So having said that, K is 20, N is 50. So you really have 0.2. 20th percentile is 0.2, if you will. 20th percentile. Okay, remember P20. We are looking at P20. P20 is what? 0.2. 20th percentile. 20 over 100 or 0.2 or 20%. So I want to make sure that everybody understands this part comes from the fact when we say P20, it means what? We are dealing with 20%. That's how we get 20. So it's really not that big of a deal again. Times 50, and it gives us a whole number. Because it is a whole number, you locate that, you use the next one, you take the average of the two. So this is the 10th one, 6.2. And the next one is 6.5, add them up, divide by 2. I want to make sure everybody understands what's happening here. We are dealing with a whole number. Look at the procedure, step number 4. Because it's a whole number, we use the next one as well. Part B, 87th percentile, or 0.87 times N. 0.87, however you want to put that. And so you end up with 43.5. Again, I'm going to emphasize, class, 43.5 or 43.1 makes no difference. You go up to the next one, 44th piece. You need the 44th piece. So you got to count, and here's the 44th piece when you do the counting, or you can go down, it's easier, go down from 50. And the answer is 28.5, and you use the proper units as given. There is one more topic we want to cover, measures of relative standing and box plot. So we're going to look at quartiles.
Quartiles are measures of location denoted Q1, Q2, and Q3, which divide a set of data into 4 groups with about 25% of the values in each group. Quartiles separate the data into 4 equal groups. Q1 is equal to P25, Q2 is equal to median, and Q3 is equal to P75. Q1, the first quartile, or P25, separates the bottom 25% of the sorted values from the top 75%. Q2, the second quartile, or P50, and same as the median. It separates the bottom 50% of the sorted values from the top 50%. Q3, the third quartile, is the same as P75. It separates the bottom 75% of the sorted values from the top 25%.
I can't really emphasize this enough. There is no universal agreement. There are, if you use different technologies, you may get answers that are slightly different. Deciles, they cut the groups into 10 equal pieces. Inner quartile range is defined as Q sub 3 minus Q sub 1. To find them, we arrange the data in order from small to large. We find the median. Median is identical to Q sub 2. Now, one easy way to find Q1, again, you can go through the process of percentile. We just did that. or you can go with the easy way out. Cut the data into two pieces, the bottom half, find the median becomes Q1, the top half, find the median becomes Q sub. You can find the percentile when it comes to Q1 and Q3. Q2 is just a median, it's very easy to find. And you can go through the process, or you can take the easy way out as mentioned here. Here's a simple example. We are repeating the same example. We want to come up with 5-number summary. So the question is, what is a 5-number summary? A 5-number summary is just 5 numbers. The easy ones would be the first and the last one, minimum and maximum. Then we have the first quartile, Q1, the second one, or the median, Q2, and the third one, or Q sub 3. So we want to find that. Now, we want to find those 5 numbers. First, let's go with the easy ones. This is the minimum. This is the maximum. Now, the next thing is the median. There are 50 pieces of data. We have 25 and 25. Therefore, the median is somewhere between these two. This is the same as Q sub 2. You have two choices. Q1 is the same as P25. You can go through the process of the previous examples and find P25. Q sub 3 is P75. You go through the process and find it. I don't want to do that. I want to go with the easy way out. What is the easy way out? Look at the bottom half only, assume the top half doesn't exist. So you have 25 pieces of data. For the bottom half, find the median. That's Q1. You have 25 pieces at top, find the median. That's Q sub 3. Let's look at the last question. So we got the 5-number summary, the numbers that we just came up with. Now we want to do a box plot, or a box and whisker plot. Is a graph that consists of a line extending from the minimum to maximum value and a box with lines drawn at the first quartile, Q1, the median, the second quartile, and the third one. In other words, I'm going to draw something and I'm going to erase it. I want to give you the concept. So the concept is very simple. You need to go through this procedure. Find the 5 numbers. We already have the 5 numbers. Now, it says construct a line segment extending from the minimum to maximum. You'll see the whole thing put together in a moment. So this would be the minimum. This would be the maximum. Or you can extend that with a number line and just put the minimum and maximum there. It is extremely important to do it within a proper scale. So this is the value of the minimum, if you will. So where you see min, you draw a tick mark like that, a tick mark like that. Then that is the line that extends that. Then you put Q1, Q2, Q3, and this is the whisker, box and whisker plot. But let's see a proper one. I just gave you the concept. So here's how you do the drawing. So this is how you find the whisker plot. Just make sure it's to scale, and you may have a number line at the bottom. You don't necessarily have to start the number line from 0.8. You may start from 0, and let's say you go to 80, or 0 to 100. And then you're interested in 0.8 and 77.8 as the min and max, and the rest of them in between. And this happened to be skewed, by the way, to the right. The tail is on the right, it's skewed to the right. Now, let's answer the final piece. Outliers. Do we have any? Here's the process. We have to find IQR. IQR by definition is Q sub 3 minus Q sub 1. So we calculate that. Now, anything less than Q sub 1 minus 1.5 IQR, anything smaller than that, or anything larger than Q sub 3 plus 1.5 IQR, they are outliers. So all you have to do, look at your data, and you see you don't have anything less than negative 12.5. So look at 41.9, and clearly 43 is larger and everything after that. Therefore, they are considered as outliers.